this is my group's Lab 4 Fluent project. So the first thing we're going to do is go into geometry, change it from the analysis type 3D, and then select 2D. And what I did is I imported it from SOLIDWORKS. So I'm going to open it up in Design Modeler just so we can see the geometry really quick. Here's our wind tunnel, and here's the flat plate that we added into our wind tunnel. We made sure we included this angle on the front of the plate to make sure that the forces, drag force coefficient on the top plate is calculated more accurately. And this is also what our TA said to do. So now we're going to get out of this and go to meshing now. Now we're in the ANSYS Fluent Mesher. So the most important things in this section is we're going to have to name the top plate, as you see right here. We have the bottom plate also named. We have the velocity inlet named, the pressure outlet, and then the walls named. And then we want to create our mesh. In this case, all we did was do a edge sizing. So edge sizing goes on all four of these edges right here, and we made the element size 0.00015. And then for our mesh, the standard element size is 0.001 meters. And just to make stuff easier, turn on batch connections and also change the mesh type to triangles. It'll allow for a quicker solution. And this is what the mesh looks like after it's generated. After you're done this, you can X out and go to the solution. So make sure you add double precision, and then depending on how many processors you have, you can add more processors. It'll allow for quicker solutions, and just hit start. And now we're in the solver. You can see right here, this is our mesh for the wind tunnel on the flat plate. So first thing you want to go is go into the model. And in this one, it's up to you. We did K omega. You could also do K epsilon. Don't hit laminar. Laminar's for a perfect case. And in our project, we're going to have a laminar and turbulent region. So for that reason, do either K epsilon or K omega. So you can hit OK for that. Next thing, you want to make sure your inlet velocity is set to the correct one. So this is our correct value. You can get this by, in the project, they'll give you a specific hertz for your test section. You can multiply that by the equation they gave you to get your velocity for your test section, and then use the contraction ratio to get your inlet velocity. Make sure you hit apply for that. And then for future calculations, you want to change your reference value. So change your length to 0.229, which is the length of our flat plate. This is in meters. And then you could change your velocity meters per second, because this is going to be referencing your test section. If you don't change this, it's going to be referencing your inlet velocity, which will give you a wrong answer. So next thing we'll do is we're going to hit initialize. And once this is done, we'll then calculate. So run calculations, and then I just put 100 iterations. However, depending on your mesh and everything, it might take more or less. Hit calculate. And once your calculations are complete, we can start with part A, which asks for finding the velocity contour as well as the vectors. So to do that, we'll go into results, hit graphics, and go into contours, and select the contour. Set your contour to velocity, and then make sure you set it to velocity magnitude. Hit compute, and then save and display. And then right here you can see our full velocity magnitude for the wind tunnel on the flat plate, and we can zoom in so you can see the boundary layer velocity here. So next thing we're going to do is we're now going to get the vectors for the velocity contour. To do that, we're going to go right here into the results section and go into vectors, open that up, select it, and set it to velocity, and then color by velocity and velocity magnitude. We're also going to hit compute and then save and display. You can see here we have the velocity vectors. We can zoom in on the plate itself. As you zoom in, you can clearly see these triangles that are representing the vectors for velocity, so magnitude and direction. Now we're going to continue to part B, which asks us, actually we're going to skip part B for now because we'll solve that in post. I'm going to then show part D and part E next. So to plot variation of wall shear and then plot variation of local skin friction coefficient, all we're going to do is we're going to close this out. We're going to go into plots, go into XY plots, and in here we're going to change the y-axis function from pressure and go into wall fluxes. And then in this first one, we're going to do wall shear. You can see there's wall shear stress, wall shear in the x direction, wall shear in the y direction, and skin friction coefficient. We're just going to do wall shear stress for now. And we're going to select the top plate because that's what we're specifically looking at, and we're going to save and plot it. See, this is our wall shear stress on the flat plate. Next, we're going to do skin friction coefficient. So same place, make sure you have it on wall fluxes, and then just change this drop down to skin friction coefficient. Make sure you still have top plate selected, and then save and plot. And here's that graph. And next thing we're going to do is we're going to find the drag force coefficient on the flat plate. So there's two methods to do this. One method is you go into reports, go into forces, hit top plate, or if you want to do the entire plate, do top and bottom plate. But for right now, we're just doing the top plate. And you're going to go and print this. So you're going to get this force report right here in the console section. And your coefficient of drag is going to be this last value here. If you wanted to be more clear and have it where it actually says CD is equal to etc., whatever number you have, what you could do is you can go up into solutions and go to report definitions. You could create a new one, go to forces and hit drag, select drag coefficient, and then select whatever one you want to measure it on. In this case, we're going to do top plate, and we're going to hit compute. Okay. Going to close it out, and now you can see it printed the CD for the top plate in that exact value, which matches the earlier value we looked at. So that's how you find drag force coefficient. So the next thing we're going to do is we're going to go into CFD post. So we're going to X out of this, save changes for current and future calculations. We're now going to go into results. So we're now in CFD posts. So you can see when I zoom out, here's the wind tunnel. Here's our flat plate. And so what we want to do is find the velocity vectors, or sorry, the velocity profile for these three positions. So for these three positions, it's going to be 0.2 centimeters, this is going to be 8 centimeters, and this is going to be 16 centimeters. It's the first thing we want to do is we're going to go and hit you're going to hit this and insert a chart. You can name this velocity profiles. I've already have it made. See here, velocity profiles. And so the main thing you're going to do is you're going to need to make some data series. So to make data series, you're going to go to insert, go into location, and then select line. And you can hit OK. And here you're going to put your x values for 0.1 and 0.2, and then in this box you can put your y values. So what this is going to do is it's going to put your x values are for line 1 is going to be here, x value for line 2 is also going to be here, and then for your y value for point 1 it's going to be right on the top of the plate, and your y value for point 2 is going to be up here. And that's how we're going to measure the velocity profile for this position. You're going to then duplicate that, and what I mean by duplicate, you just click on your line, you're going to hit duplicate, and from there you can then program these values. You can then go back into your velocity profile, and then you can add these by clicking this button right here, and from there you can hit location, and these should show your lines that you just created. With those lines, the first thing we're going to do is we're going to make some expressions. So expression you're going to need to make is going to be a u non-dimension expression. So you could type this in, velocity u, and then you divide it by, in this case, this was our velocity. So we divide the velocity by our test section velocity, and that helps to non-dimensionalize it. Same thing with your y direction. You can also do the same thing. In this case, in the y direction, we divide by the plate length. So your height divided by the plate length. And then to later compare with the Blasey solution, we're also going to have to make this expression, eta expression. You can ignore, in this case, the 0.0013. This is just due to my origin being at a different position. So this is shifting my origin back to 0 for the y-axis. You can see that the same thing is happening here. So you don't need that. However, you're going to have to do y divided by the square root of, in this case, your viscosity. Make sure you put your units, so meters in brackets, and then you multiply by your x value. This will help us compare the Blasey solution to these velocity profiles. We're then going to go back into the outline. For your x-axis, you want to change it to your u non-dimension, so your velocity non-dimension value. And then for your y-axis, you can change it to eta. We can now apply these. And you can see this graph is a little funky right now, so we're going to cut it down to be more accurate. We're going to set it to 10 for now in the y-axis. Apply. And these are our velocity profiles. And then to add another one, I already have this one made, so you guys are going to have to make this in Excel, but you would just hit add new, and then for me, I already have it saved as a CSV file, so I just hit import, and then I would import the Blasey solution, and I would overlay it onto this exact same chart. So that's how you do the rest of the Fluent project. Thank you, and have a good day.